Hello everyone, welcome back to the channel. I hope you guys are doing amazing. So today we are going to start the dynamic programming playlist from the very basics. So when I was learning DP, I tried to search YouTube but I couldn't find a single playlist which taught very basic stuff like 1D DP, recursion memoization, and went all the way till Bitmask DP. Even the famous playlist one on YouTube does not teach the whole thing, right? Bitmask DP, these things also many times comes in the placement examinations. So I am on my mission to make the best possible DP playlist. So even if you are a beginner or an intermediate or an advanced guy in DP, you can follow my playlist. If you are beginner, you will definitely learn from the basics, right? And if you are intermediate, you can just revise the concepts and have a lot of practice problems also. And if you are advanced player in DP already, you can look at some good problems, and definitely a lot of practice will be required before your placement. So yeah, you can even follow this and share it with your friends. Let's start. Let's see what are the topics that we will be covering under this playlist. So first of all, we will start with the basic. We will start with the intuition of this 1D DP, and we will just see recursion, we will see memoization or catching, how we can optimize things, and then we will go to the iterative DP or bottom-up DP. We will have some practice problems. We will then move on to Knapsack DP, where we will primarily learn the take not take approach. This approach will help you to solve a lot of problems. Then we will see DP on grids. We will see some common variations of DP on grids. Then we will look at DP on strings, which involves DP on subsequences and palindromes. We will learn a new concepts, very new, interesting and new concepts in this portion. And we will also go through some common problems like longest common subsequence, longest increasing subsequence, and edit distance, and many others. Then our next topic is DP on trees and graphs. The common approaches we will study, as well as the intuition. We will look at the practice questions. We will also see some off-topic stuff like binary lifting, which is DP-like, which sometimes comes in the placement exams. We will also go through Bitmask DP, Digit DP, and then DP on algorithms also. Now, if you have done a lot of DP, you will understand that in many places, thus using DP is insufficient. We use DP with binary search, DP with sliding window, DP with prefixes. We will try to cover almost many variations of these problems. Then we will move on to partition DP, which involves a mathematical concept called matrix chain multiplication. We will explain this in details, and then we will also move on to some 3D DP patterns. Okay. So yeah, these are all the things that we will do. And in today's video, I will try to cover this basic intuition and also this 1D DP thing, right? So let's just start quickly. Okay, so first we will understand what the word exactly this dynamic programming means. So dynamic, what does the word dynamic means? Something which changes with time, right? Something which changes with time. Okay. Now in context of coding, what is time? This time is nothing but if you are writing a for loop, you are initializing a variable 0 and going till n, then this time is nothing but this variable I. Okay. So there is a concept of state of a DP which is defined by this I, and we say that there is a transition within this I to some I plus 1 or I minus 1 according to the problem. Okay. So within time, so if in I minus 1 there is some state, in I there is some state, there I plus 1 there is some state. State of a function changes according to time, then it is like dynamic programming. Okay. So this is a very abstract type of thing which I told you, but what exactly does it mean? And like you must have heard, it is very much related to recursion. So how exactly we can write recursive DP or iterative DP and stuff like that? So first thing which we will learn, which everyone learns in the DP, is that Fibonacci numbers, right? So if you, I think you already know about Fibonacci numbers. Still, I will just say it. The numbers which are part of the series, starting from 0, 1, 1, 2, 3. So it is nothing but the nth term is given by the sum of the previous two terms. So 3 is the sum of 1 plus 2. Next will be 3 plus 2. Next will be 5 plus 3, 8. Next will be 8 plus 5, 13. The next one will be 21. Next one will be 34, and so on. Okay, and so on. So this first term, this is not the first term, this is known as the zeroth term of Fibonacci. Remember it. If it's F0, not F1. This is the first term of Fibonacci. Okay. Also, this is the sixth term. You can just count. This 8 is the sixth term of Fibonacci series. Okay. So basically, what is our task now? What I will say that what should be your next task to do? So the task which you need to do now, write a function to find nth Fibonacci number. Okay. How you will write this? How you will optimize this? So you can do something like you know that the first term Fibonacci of, if I tell you Fibonacci of n, you need to calculate Fibonacci of n, right? You can easily know that the recursive relation is given by Fibonacci of n minus 1 plus n minus 2, the previous two terms. Okay, sum of the previous two terms only. So the thing which comes to mind now is that how, when it comes to writing the code, I can write a function, let's say int Fibonacci. Okay, I can write a function in Fibonacci. Okay, so whatever code I will explain, take it as a concept. Don't take it as a language like C++ or Java. If you can understand the concept, definitely you can write it in your own language, right? So try to understand the concept only. So we can return easily something. First, we need to write the base case. So if we are writing a recursive function, if you are trying to write a recursive function, what will happen is that you need to write the base case first. So what is the base case? Previous two terms is already required for calculation, right? So what about the first two terms? So first two terms, it comes as the base case. So if n equals to 0, I can write just return 0, right? Now if n equals to 1, I can do simple like just return 1. Okay. Else you just return Fibonacci of this n minus 1 plus Fibonacci of n minus 2. Now, if you try to draw some recursion tree, in order to understand what will be the time complexity of this code. Okay, to try to draw some recursion tree. Now, what do I mean by it? Let's say you are going to calculate some sequence, right? Let's say you are going to calculate a number, Fibonacci number, let's say Fibo of 6. Okay, I told you to calculate Fibo of 6. What will you do is that you will say, to get Fibo of 6, I need two things. Okay, I need Fibo of 5. I need Fibo of 5. So let's write Fibo as f of 5. Okay, I need Fibo of 5. Also, I need Fibo of 4. Okay, now to get 5. Okay, so if you want to calculate something called Fibo of 6, you will tell me for this 6, I need the previous two terms, which is Fibo of 5 as well as Fibo of 4. Isn't this? I need the previous two terms. Now for 5, all I require is term 4 and term 3. I am just going to the terms and adding them, right? In the recursion, what will happen? With 6 will call 4 and 5. 5 will call 3 and 4. 4 will call again 3 and 2, right? I'm trying to draw a recursion tree. Then this 3 will call 4 will call 3 and 2. 3 will call 2, 1, right? You can easily understand these stuffs. 3 will be calling again the same 2 and 1, and this 2 will be calling nothing but 1 and 0. Okay, 1 and 0. Then again this 2 will call this 2, and this 3 also. Okay, but 1 and 0 will be returned. Okay, 1 will return 1, 0 will return 0. So when it will return some 0, as it will also return 1, it will just add those two terms and get the Fibonacci of 2 to be 1. This Fibonacci of 2 is, let's say, 1. It will return 1 here. It will also return 1 here. So Fibonacci of 3 will get 1 plus 1 and get added to 2. Similarly, Fibonacci of 4 will get this 2 from 3 and 1 from this Fibo of 2 and get itself convert to 3. Similarly, it will go on. And this will get 5 from here if you calculate, and it will get some 8. So it returns 8 as the answer. Now you see, you are calculating this fib of 5. Let's say it's the first time. 4, again, it's the first time you call it. Then this 4 is duplicate, right? Let me circle out the duplicate ones. Let me use some color and circle out the duplicate ones. So this is the duplicate one. Okay. This is not the duplicate. This is the first time it is called. This is also first time it is called. Then also this is fib of 3. It is first time called. Then this 3, again it's the duplicate one. This 2 again is the first time. Okay. This is again the duplicate one. Let's say this 1 and 0 are also the first time they are called. Then you see the remaining all the leaves, all the nodes of the tree, remaining all the nodes of the tree are the duplicate node. So what do I mean by this? What do I mean by this when I say as the duplicate nodes and stuff like that? We are saying that when we have calculated this Fibo of 4, we are just wasting our time by calling Fibo of 5, because Fibo of 5 again calls Fibo of 4. So why don't we take this Fibo of 4 from somewhere? Why don't we take this Fibo of 4 from somewhere? So here comes the optimization step, which happens, which is also known as memoization. Okay. So the concept is really simple. It's pretty simple. What we do, this 0, we consider some array. Okay. For every, listen to this carefully, because for all 1D DP, 2D DP, every problem you do the same way. Okay. So you have an array. Okay. Now what you do is that you say that the ith term of my array gives my Fibonacci of I. Okay. The ith term of the array gives the Fibonacci of I. So let's say this is the first term. This is the 0, Fibonacci of 0. Okay. This is the 1. Now these two are the base cases. First, what you will do, you will keep an array. Okay. This will give me, let's say, Fibonacci of 6 as I calculated. You will store every element initially as -1. You will initialize all the element as -1. Why -1? Because it shows, -1 shows that the array is empty. The array is empty. Just to show the array is empty, I'm using -1. So when you will reach, let's say you are reaching Fibo of 4 for the first time, you will see that there is a -1 present. Let's say Fibo of 4 is somewhere here, and there is a -1 present. Okay. So what will happen is that it will, whether it is if it is -1, then replace that by Fibo of 4. Okay. Replace that by Fibo of 4. If it is already something Fibo of 4, then when it comes to again calculating, it will check that it is not -1 anymore. So if it is not -1 anymore, if this, whatever this array, ARR or DP array, you can say, okay, I'm telling that this is nothing but a DP array. So you can check that if this DP array is this I is not equal to -1, what you do is return DP of I. So it means that I will return the value. I will just return this same value if duplicate it is. If it is found duplicate, I will not waste my recursion again and again by doing it again. I will not just build up my recursion stack over and over again. Okay. So this is meant by memoization, or this is also known as caching. This is sort of acting as a cache memory. If you know about cache memory, this is acting as a cache memory. If the calculated value is already present, do not calculate it again. The thing which it tells is this simple. If the calculated thing is present again, do not calculate it again. Okay. This is simple. Okay. Okay, the notes in the class, I will provide it as a PDF form, okay, in the description. You can get that easily. So now how can you put forward to this optimization? Okay, what will you do? Okay, so this is something you got it. I guess memoization is something you got it. It is also known as caching. To improve further, what you do is that you use the iterative method. Okay, you use the iterative method. Iterative Fibonacci. It also uses the same DP array. What it does is very simple. In this case, you can understand it to be very simple, but always it will not be so. Why and how? For iterative DP, what you need to do, you need to find a state I. Here the state I is nothing but the index. Okay. And for the first thing to convert any recursive DP, I am just writing some steps. This is true for everywhere. So you can note these steps down. This will help you understand, right? Later you will be like, you will realize how much helpful it is. Steps to convert memoization to iteration DP. Memoization or recursive DP. Recursive, you can say that recursive DP I am converting to iterative DP. How to do that? For any DP problem, it may be 1 DDP or 2 DDP. What will you do is that first you will write the base case. Write the base case, okay? Write the base case, okay? When you got the base case, you will fill it in the DP array. So here I already told you the base case was first element is 0, the second element is 1. This was the base case, okay? Now, what you need to do next is copy the recursive formula. Copy the recursive formula, okay? But how you need to copy it? Many times you need to copy it from the back of the array. Many times you need to copy it from the back of the array. But in this case, this is a really simple case. You can easily understand that you can just start a for loop. You can just start a for loop starting from here. Let's go from here and just go to the end of the loop. Go to the end of the loop. And all you need to do is that in every iteration I, you just do dp of I, nothing but dp of I minus 1 plus dp of I minus 2. You can do as simple stuff as this till n. At the end, return dp of 0 or dp of n, whatever. Return the answer. You need to visualize that where is my answer present. If I am finding the nth Fibonacci term, then my answer is present in the last term. And for the Fibonacci series, I will return this dp of n. I will return this dp of n. Okay. So let's try to see the code for this. Okay. Let's try to see the code for this. We will solve in the Leetcode. And yeah, and like just check. Let's just check the. So what we can do is that is simple. If we can say that if n is equal to 0, first we return 0. I'm writing the base case, right? If n is equals to 1, all you do is you return 1. Otherwise, you return Fibonacci of n minus 1 plus Fibonacci of n minus 2. This n minus 1 and n minus 1 will again call n minus 2 and n minus 3. Again, this n minus 2 will call 3 and 4. And when it reaches 0 or 1, it will just return this 0 value and 1 value, and it will keep on adding each iteration. And when you just do this, see, n is only 30. N is only 30. So that will work here. That will still work here. But time complexity will be not so good. So how we can optimize this? Okay. So how to optimize this? Check carefully. What we need to do is write another calc function, which is nothing but int n. It takes int n and another vector also, which we will call as dp. It saves the state in this vector. And what we will do is that you check the method. It's simple. For every conversion of recursion to memoization, to recursive DP, you just need to just copy the base cases. Write this line whether if dp of this n is not equals to -1, return dp of n. I'm telling that if it is empty, if the dp array is already empty, what you will do? Then only you go proceed further. Otherwise, you just return the value of n. If it is not empty, then save the state. Then you must save the state. And what will be this state? This is nothing but calculate n minus 1 plus calculate this n minus 2. Okay. So this is the exact same as this. Okay. I'm practically copying this here only. I'm just feeding one extra argument. Now, all you do is return dp of n. Okay. All you do is return dp of n. Now, what you need to do in this function is have a vector. DP initialized n plus 1 because this is, we are calling it till n, so n plus 1, and initialize it with minus 1. Now what you need to do is that not for you just do return, you just do return calc of n comma dp. Okay, you pass this dp and n, just call this function. This function will do all the things and return. All you need to do is pass this dp array. You see, we have the accepted thing. Our runtime complexity will be better this time. So now, in order to convert from this recursive DP to iterative DP, what you need to do is very simple. I told you there were 3 steps, right? What were these 3 steps? So they were: write the base case, copy the recursive formula, and then return. Okay, write the base case, copy the recursive formula, and then return. These are the 3 things you need to keep in mind. So the copy, for copying the base case is nothing but dp0 is 0, and all you do is like dpn, dp1 is 1, right? These are the base cases. Then write the iteration, copy the iteration. Why I am telling copy? Starting from I equal to 2, as I told you that 0 and 1, for calculating the ith state, we need the -1 and -2 state also, right? So for 2, from 2 we start, we go all the way till n, and all we do is now dpi is nothing but is n-1 and n-2. So what I'm doing here is I will just take this, copy this, and take the dp. So you might think that if I need to change so much, why did I just copy it? You will understand this later, because for big problems, all you need to do is just copy this recursive dp to this iteration formula. Okay, to this iterative formula, you just need to copy the recursive dp. That will all be the case. That will all be the thing. If you just see this dp of n, you can just return as the nth Fibonacci number. If you try to run this, you see we have the accepted thing. If you try to submit this, so this is okay. So if it's 0, if it's something 0, return 0. So if n is 0, then you cannot access the dp of 1, right? If n is 0, all you do is return 0. Okay, all you do is just return 0. Will this work now, or does it still give any error? Let's try to check. Yeah, we have the accepted things. See, the runtime complexity is also better. I hope you understood this from the conversion from recursion to memoization to iterative DP. Same thing, we will do another practice problem. Minimum cost in climbing the stairs. Okay, so let's read the problem. It's Leetcode 746. It says the minimum cost to climb stairs. You are given an integer array cost where cost of I is the cost of the ith step on the staircase. Once you pay the cost, you can climb either 1 or 2 steps. You can start the step with index 0 or index 1. Return the minimum cost to reach the top of the floor. Okay. So what you need to do here? What exactly do you need to do here? Let's try to visualize. Okay. Let's take a new page, and we have now what we have is Leetcode 746 problem. We have a question 746. Okay, in this problem will be a better understanding of DP, actually that bottom up thing or iterating from backward, because Fibonacci was like quite easy. This is also really easy, but for the basic concepts, this is a okayish problem. So what it is told, say you have an array 1, 15, 20. These are nothing but steps of a staircase. This is the 0 step, this is the first step, this is the last step. Okay, you need to reach the top floor. Top floor is nothing but I equals to this n. If this is I equals to 0, this is thus I equals to n minus 1. This top floor is nothing but this I equals to n. Okay, so what you need to do, you need to reach this I equals to n. You need to reach this out. Okay, if you, what is the cost, what will be the minimum cost? You need to find the minimum cost. Okay, minimum cost to reach 2. Okay. Also, the starting thing you can start with either with index 0. You can start with either 0 or 1. You can take a single hop or a double hop. Now, the thing is that the intuition is that this you will always, you cannot do this greedily, right? What do I mean by greedily? When I say is that suppose you are thinking that always I will take 2 steps and reach the end faster in minimum cost. That is not correct, because it may be possible that by taking 2 steps you are getting into some value which is much more, which is much more. So you cannot do that. It might be optimal to just take 1 step and then take 2 steps, so that you can avoid the number which is having a more cost. Okay, it is always possible. So what you do is that in this case, what you do, you just jump it to the next iteration. There is also another case given in the Leetcode. If you check, this is quite good case. The cost is 1. First you take a cost of 1 and then jump 2 places. So you go from here to here. Then again you jump 2 places since it's here. Then again you jump 2 places to avoid this 100. Okay. Now if you jumped again 2 places, you will get into this 100. There will be a problem. So what you do is that you jump 1 places now only, and then go to do the jump 2 places again. Once you reach here, or you can just jump and go ahead. You can just jump 1 and go ahead. If we are the second last element, then also you can just jump and go ahead. So see, you reach the top. That is, you reach the ith value in the cost array by only paying this 1 rupees, 1 rupees. You only pay this 6, right? So the thing which is here is that you need to visualize that I need to take care of the future. I need to take care of the future steps. Okay. So what can be a recursive solution to it? So let's say we write a function int mean cost, which will take this cost array. Okay. And which will have a state I, and this mean cost will give me what is the minimum cost to reach the end of the staircase, to reach the top of the staircase from this index I. This gives minimum cost to reach top from ith position. Okay, what is the minimum cost to reach top from ith position? So now what you can do is that you can start with 0 or 1, right? So whichever is the minimum, that only you will return. So you can do like minimum cost. You can call this minimum cost function and tell me that start from 0, also start from 1. Do both of the things and check whichever give me the minimum value, just return that. Okay. Now what should be the base case of this recursion? The base case, first base case, you see, if you write this if I equals to n, or greater than equals to n, in fact, if you are in the last step, you can jump 2 places also, right? So you might reach more than n, maybe reaching more than n. That is also valid. So if you are already, if this ith step is already at the top, and greater than equals to n is already at the top, you return 0. So if you are already at the top, you just return 0. You don't need, there is no cost you incurred. Okay. Otherwise, what you will do? You do is very simple. What you do is take 1 step. You can options 1 step. Okay. Another option, take 2 step. If you take 1 step, you need to give the cost of which your current index at. Then again, you need to call this recursion cost and take 1 step, I plus 1. I have taken 1 step means I have gone to the next index. You do understand this, right? For this 2 step, the same thing we need to do, just I plus 2. Because now I have taken 2 steps and I am in the second index. Now this will again call I plus 1 will be replaced by I plus 1. So this I plus 1 will be treated as I now, and it will again call like from there it will check whether I can go to I plus 2 or I plus 3. Okay. So after checking this, whichever is the minimum, I will just return that. Isn't it very simple? What did I do exactly here? is that in every step I am checking whether I can take one step or two step. Okay. Then yes, let's say I take one step. Then from that again I will check, I can take one step or two step till I reach the end. Till I reach the end, and this cost will get accumulated with this minimum cost. Again, it will keep on accumulating. Now for this position, suppose I have taken one step and some other variations of the other step will give me the cost of taking one step. This also will give me the cost of taking two steps. Okay, so I've taken both one and two steps. One and two steps I've already taken. Whichever is the minimum, just return that. Whichever is the minimum, just return that. In every step, it will keep on doing that. Whichever is the minimum, just return that. Okay. If you see n is not at all defined here, so I just quickly define n. Okay. Yeah, we do have the accepted thing. Let's try to submit it. You will see since n is 1000 here, the time complexity is 2 to the power 1000. I told you the recursion tree is the time complexity of this recursion tree is 2 to the power n. There are n nodes in the recursion tree. 2 to the power n nodes in the recursion tree, right? So what you need to do to convert this is very simple. It's very simple. Same thing you will do. Write a DP. Write a DP. Okay. Okay. Uh, yeah, it just returns. So recursive DP, you can leave it n minus 1 or n plus 1, whatever. You just write a DP. Initialize it with n minus 1. Okay. Pass this DP function. Pass this DP function everywhere. Pass this DP function. After passing, just quickly pass it everywhere. Okay. Now, what you need to do is very simple. Start from this. Check if DP of I. If it is not minus 1, just return DP of I. Simple. Okay. It's quite easy. Now, if it is minus 1, you save the state. You save the state. What state you will save? You will save the result. You save the result. Okay. And return DP of I. Just return DP of I. This is all. This is all you need to do. And see, this is very manual, right? I did not write any much of extra code or something like that, right? I did not do like really great stuff. Anything great, I did not do it. I just wrote the recursion, which is very intuitive, and I followed some mechanical step to arrive at something, some memoization kind of thing. And you see, from TLE we have accepted. And you will see from TLE we have the accepted thing. We have the accepted thing from directly from the TLE. Now, the 3 steps, as I told you, which you need to do to convert this into an iterative approach. So, what you need to do, it has already been accepted, right? But the interviewer may ask you to write the iterative DP or the bottom-up DP, right? So, what you need to take care of this. So, you write the base case. First thing, you will write the base case. What is the base case here? Here, the base case is nothing but DP of n is 0. See, the DP of n is 0. You reach the last one, you don't have to give any cost. Also, DP of I here, I told you already. DPI denotes cost to reach end to reach top from I. Okay. What is the cost to reach top from the last index? Is nothing but the cost itself, right? If you are already at the last index, you do not have any choice. You have to just pay the cost and go ahead. Just pay the cost and go ahead, right? So you just keep the base cases there. Just keep the base cases here. Then you form an iteration. Here the iteration should be from -1 because you see, you require DP of I plus 1 and plus 2. Okay. And from n minus 2, if you start, then only from plus 1 you get n minus 1 and plus 2 you get n. Both of the values are present in the base case. Therefore, you can start this iteration. This is the reason why this time it's known as bottom-up DP. Bottom-up. In 2D you will see that it is going from bottom to top. Here you are seeing that it is going from right to left. Okay. quite simple. Next thing is now copy the recursion step. Copy the recursion step. What you will do is copy this. DP of I is nothing but cost of I. I'm writing the exact same thing if you see. Cost of I and the minimum of these two. Minimum of DP of I plus 1 plus 2. Okay. This is all you have. This is all you have. This is just all you have. You need to check definitely whether starting from 0 gives me the optimal result or starting from 1 give me the optimal result. Whichever will give me the most optimal thing, I will just take it. I will just take it. Let's try to run it. You see, we don't need this function at all now. We don't need this function at all. So you check. We have the accepted thing. If you try to submit it now, so see, we have the best runtime complexity with 100%. So see, this was all, I guess. It's really simple. As I told you, just need to follow few steps. Now, all of this might look quite easy to you, but still, I would like to share you one important tip is that, okay, you learned everything. You should learn everything for interview purposes. That's okay. But in online exams, what you can do in online tests. So as I told you, you need to write recursion first. If you are expert already, you just can write recursion directly iterative DP. But always start with recursion first. Go to memoization. Then go to iteration. If you can think of the DP states directly, you can just directly write this. Okay. Otherwise, you can follow these steps to go. In online tests, it is sufficient. You got daily at recursive, but both memoization and iteration got accepted, right? So it is sufficient. What you can say is that it is sufficient that to stop at this memoization step or this recursive DP. Memoization is also known as recursive DP because it will always give you an accepted answer. It does not give you TLE anywhere. It is only because of the stack memory which the interviewer may ask you that you need to write the iterative. So yeah, we have it. So these notes will be available in the as PDF form. And as I told you, I think this intuition of 1D DP is done, recursion, memoization, these concepts are already been taught, this iterative DP also. And we will definitely do some practice problem, but we also from the next video, I will start with the Knapsack DP and learn the very important take not take approach, which will help you to solve many DP problems. And yeah, so that's all for this video. Definitely share this video, like, subscribe to my channel. Definitely do share it with your friends, yeah. Definitely, so that I also get some motivation. And if you are excited about this playlist, type let's go in the comment section so that I get to know that you are excited about this. And let's just do it. Let's just do it. That was all for this video, and I hope you have a good day ahead. So yeah, that was all. Thank you so much. Thank you so much.